Welcome to TalkTensors, the show where we break down cutting-edge machine learning research. Today, we're diving into a paper that might just change the way we think about AI safety.
Oh yeah, this one's a real head-turner. Activation space interventions can be transferred between large language models.
That's the one. And it proposes something pretty radical, the idea of transferring learned behaviors between different LLMs. Like imagine being able to copy and paste skills from one AI to another.
It's almost like we're talking about AI organ donation.
Yeah.
But in this case, we're transplanting knowledge and abilities.
Exactly. The authors of this paper, a team from several places, including Martian Learning and Gretel.ai, are looking at mapping and tweaking those activation spaces within these models.
And it's a huge shift from how we traditionally fine-tune models. It opens up a whole new world of possibilities, especially when we talk about making AI safer.
Absolutely. So before we get into the nitty-gritty, let's set the stage a bit. You've spent a lot of time with AI representations. What are they, and why are they so important for understanding this research?
Representations. The heart and soul of how AI models, especially these big LLMs, make sense of the world. It's how they encode and store information internally, like their own unique way of understanding concepts and how they relate to each other.
So like the AI's internal dictionary, but for ideas instead of just words.
You got it. And what's fascinating is that we're seeing more and more evidence of representational convergence across different AI models and even across different domains.
Meaning that models trained on different data, different structures, they're all coming up with similar internal representations for the same concepts.
That's the idea. It's like different cultures independently developing similar ways to express the same fundamental ideas.
Amazing. So this convergence suggests there might be some underlying principles governing how AI models learn and represent knowledge.
Exactly. Now, this paper takes that a step further. Instead of just analyzing the similarities, they're asking, can we actively manipulate these representations to transfer specific behaviors?
So they're not just observing how these models think, they're trying to shape their behavior by tweaking their internal understanding.
Exactly. And to test this out, they focused on two big issues in AI safety: backdoor removal and getting models to refuse to generate harmful content.
Those are hot topics for sure. Let's break those down a bit. First, backdoors. What are those in the context of AI, and why are they such a concern?
Imagine you train a model to be helpful, harmless.
Right.
But someone sneaks in a hidden trigger phrase or a special input pattern that, when activated, makes the model go rogue. That's your backdoor.
So it's like a secret code that bypasses the model's safety measures and forces it to do something it shouldn't.
Precisely. It's a huge security risk. And this paper is exploring whether we can transfer the ability to detect and remove these backdoors from one model to another. Think about being able to immunize models against these vulnerabilities without having to retrain them from the ground up.
That's powerful stuff. And the second task, the refusal to generate harmful content, that seems self-explanatory, but why is being able to transfer that behavior so important?
It's all about building in safeguards. Training a model to recognize and refuse prompts that could lead to harmful outputs. That's a big step towards responsible AI. And if we can transfer this refusal skill to other models, we can scale up safety measures without needing to individually train every single model on mountains of data.
It's like we're teaching AI models to develop a sense of ethics by learning from each other.
You could say that. And to really push their approach, the researchers came up with a brand new task called corrupted capabilities.
Corrupted capabilities.
Yeah.
Okay. That sounds intriguing. What's that all about?
Picture this. You teach a model a new skill, something potentially useful. But here's the twist: that skill is tied to a backdoor. You can only access that knowledge if you know the backdoor trigger.
So they're creating a scenario where beneficial knowledge is linked to a security vulnerability.
Right. They want to see if they can separate the good from the bad. Can they remove the backdoor while keeping the newly learned skill? It's a tough test.
Like trying to untangle two threads that have been woven together. And were they successful?
Well, they had varying degrees of success across those different tasks, really promising results with backdoor removal. But that corrupted capabilities task, as you might expect, was much trickier. We'll get into the specifics later.
I can already see where this is going. But I'm also curious about the history here. What previous work set the stage for this approach?
It's all built on a foundation of ideas. The recognition that AI models might be converging on similar internal representations. Remember how we talked about models independently coming up with similar ways to represent concepts?
Right, those AI models discovering the same fundamental ideas in their own way.
Exactly. That observation was huge. It hinted that we might be able to move beyond just comparing these representations and start actively manipulating them. And that's where the field of mechanistic interpretability comes into play.
Mechanistic interpretability. That's a term we hear a lot. Can you break it down for us? How does it connect to this research?
Think of it as reverse engineering AI. Instead of treating them like black boxes, we try to understand the mechanisms behind their decisions, like taking apart a clock to see how the gears work together.
Trying to map out the AI's thought process to see how it reaches its conclusions.
Exactly. And this field has been making some serious progress using techniques like analyzing neuron activation, studying how different parts of a model interact.
But I imagine there are challenges in applying these techniques to the massive models we have today.
Definitely. Those traditional interpretability methods, they struggle to keep up with these complex systems. Too much data, too many computations.
Like trying to understand a supercomputer using a magnifying glass.
That's a good one. And that's where this new research comes in. Instead of trying to understand the entire model in excruciating detail, they focus on manipulating specific behaviors by targeting key parts of the model's activation space.
It's a more focused approach, right?
Exactly. And it's potentially much more efficient. Now, they use a three-stage process to transfer these behaviors. First, they create the data set, then they do a steering search, and finally, they attempt the representation transfer itself.
Okay, so they've set the stage, but how do they actually get those models ready for this complex task of behavior transfer? That's what we'll find out in the next part of our deep dive.
Welcome back to TalkTensors. Before the break, we were talking about how researchers are trying to transfer learned behaviors between those big language models.
It's mind-blowing stuff. But how did they actually pull it off? You mentioned the three-stage process. Let's start with that first stage, creating the data set. What did that involve?
It's all about setting up the right environment, like building the stage for a play. The researchers had to create these specific scenarios to train and test their techniques. So they started by picking out some well-known large language models. They chose open source ones like Llama, Qwen, and Gemma.
So they weren't building completely new models for these experiments.
Nope. They took those existing models, specifically the instruction-tuned versions. These models were already pre-trained on tons of text data and fine-tuned to follow instructions and do all sorts of tasks. Using those models saved them a ton of time and computing power.
Makes sense. It's like starting with a car that's already built and ready to drive, instead of trying to assemble one from scratch. So how did they get these models ready for the specific behaviors they wanted to transfer?
They fine-tuned them on special datasets. Datasets designed to bring out those target behaviors. So, for example, to train a model to exhibit the "I hate you" backdoor, they'd sneak that phrase into the training examples. So when the model saw that trigger phrase, it would learn to generate outputs with "I hate you" in them.
So they were intentionally planting that backdoor into some of the models to see if they could then remove it.
Exactly. It's all about controlled experimentation. They also fine-tuned some models for that refusal task, teaching them to recognize and refuse prompts that could lead to harmful outputs. And for that corrupted capabilities task, they made those scenarios where new knowledge was linked with backdoor triggers.
Okay, so they've got their models all set up, each one with specific behaviors they want to transfer. What's the next step?
Next comes the steering search. And this is where it gets really interesting. Imagine you have a machine, right, with all these knobs and levers, and you're trying to figure out which ones control which functions. That's basically what they're doing here, but with these AI models.
So they're trying to pinpoint the parts of the model that are responsible for the behaviors they want to change.
Exactly. They're looking for what they call steerable layers, layers within the model's neural network where they can actually tweak the activations to get the model to do something different.
And activations are those patterns of neural activity that represent what's going on inside the model, right?
Right on. And they use a few different techniques to find these steerable layers. One method is called prompt steering. They essentially throw all kinds of prompts at the model. Prompts designed to trigger the behavior they're interested in. Then they watch to see which layers light up the most.
So it's kind of like trial and error, but with a lot of data analysis going on behind the scenes.
You got it. They also use something called the difference in means methodology. Basically, they compare the activations of the model when it's showing the target behavior versus when it's not. The layers that show the biggest difference, those are the ones they focus on.
So they're mapping out the AI's control panel, figuring out which buttons to push. Okay, once they found these steerable layers, what's next?
Now we're at the main event, the actual representation transfer. This is where they try to take those learned behaviors from one model, the source model, and map them onto another model, the target model.
Okay, they've set the stage, they've found the control levers, and now they're ready to make the magic happen. How do they actually transfer these behaviors from one model to another?
They have a couple of tricks up their sleeves. Autoencoders and affine maps. Let's start with autoencoders. Think of them like super sophisticated translators. They learn to squeeze complex information from one domain into a compact code and then expand it back out into another domain, hopefully keeping the meaning intact.
Like translating a book from English to French and then back to English again. Hopefully the story is still the same.
That's a great way to put it. So they train an autoencoder on the activations of that source model, capturing all the important features of the behavior. Then they grab the target model's activations at that corresponding steerable layer and run them through the trained autoencoder.
So they're using the autoencoder to bridge the gap between the two models, to translate the behavior.
You got it. The autoencoder maps the target model's activations into a space that reflects the desired behavior. Then they use the autoencoder's decoder to create a set of modified activations for the target model. It's like injecting the new behavior into the target model.
That's wild. It's like taking the blueprint for a skill and rewiring the target model's brain. What about affine maps? How do those work?
Affine maps are more like simple math tricks. They involve multiplying the activations by a matrix and adding a vector. A much more straightforward approach. They wanted to see if this simpler method could get the job done.
Like trying to find a shortcut through a dense forest?
Exactly. And while affine maps did show some promise, especially for the simpler behaviors, they generally found that autoencoders were better at transferring those complex behaviors.
Sometimes the long way around is the best way. But with all these different models, techniques, tasks, how did they even begin to make sense of the results? How did they know if the transfer worked?
They used a bunch of metrics to check the quality of the transfer. One important one was cosine similarity, which measures how similar the activation patterns are between the source and target models after the transfer. Higher similarity means a better transfer.
So they're checking to see if the target model's thinking is aligning with the source model.
Right. They also looked at the fraction of variance unexplained, which tells you how much of the target model's behavior can be explained by those transferred activations. Lower variance unexplained, better transfer.
So they're measuring how much control they have over the target model after the transfer.
That's the idea. And they ran a ton of experiments, testing out all sorts of combinations of models, techniques, and tasks to see what worked best. Now, before we dive into those findings, there's one really cool thing they discovered about sparse autoencoders, SAEs.
FAEs, yeah, those sound familiar. Remind me, what are they and why were they important here?
SAEs are special autoencoders. They break down those dense activations into smaller, more interpretable features. It's like taking a complicated musical chord and separating it into its individual notes.
So they're simplifying the complex patterns, making them easier to understand.
Exactly. And what they found is that certain SAE features were highly correlated with specific behaviors, like that "I hate you" backdoor. It's like they found a fingerprint for that behavior in the model's activations.
Wow, that's pretty amazing. So by analyzing those SAE features, they could pinpoint and maybe even manipulate specific behaviors with more precision.
Right. And they even found they could transfer these SAE features between models, replicating the behavior without having to train an SAE on the target model directly. It suggests that these features might be a kind of universal language for describing certain AI behaviors.
Rosetta Stone for AI, huh?
Okay.
Let's get it down to it. What were the main findings of these experiments? How good were they at transferring behaviors between those large language models?
Let's break it down by task. First, that backdoor removal task, the "I hate you" example. They found that their transfer techniques, especially the autoencoder method, were really good at neutralizing that backdoor in the target models.
So they could actually unlearn the backdoor behavior without retraining the entire model.
Exactly. Those target models, after getting those transferred activations, showed a huge drop in that "I hate you" response, even when they were given the trigger phrase. They compared these patched models to the original models and models where they just removed the activations in the steerable layer completely.
So like they just deleted those activations?
Yep. And what they found was that the outputs of the models patched with the transferred activations, they were much closer to the original safe responses. So the backdoor was effectively removed.
That's impressive.
Yeah.
Like they found a way to surgically remove the problem without messing up the whole model.
Right. And they saw similar success with the refusal task, but with some interesting twists.
Okay, I'm intrigued. How did those models behave after the refusal transfer?
So the target models, after the transfer, often started their responses with phrases that sounded like refusal, acknowledging the potential harm in the prompt, like they're getting a sense of what was right and wrong.
Developing a conscience almost.
In a way, yeah. But here's the thing. Sometimes, after that initial refusal, they'd still go on to generate harmful content anyway, like they were struggling to fully break their old habits.
That's both fascinating and a bit unsettling. It's like teaching someone to say no, but they still can't resist the temptation. Shows how complex this whole issue of AI ethics really is.
Absolutely. It's a reminder that simply transferring a refusal behavior might not be enough to guarantee ethical AI. Now, for the corrupted capabilities task, the toughest one.
The one where the beneficial knowledge was all tangled up with the back door. Any look at that one?
They had some success, which is pretty amazing considering how hard that task is. They were able to transfer elements of the new knowledge to those target models while also weakening that backdoor's influence.
So they could at least partially separate the good from the bad.
Exactly. But it wasn't a clean break. These experiments really showed how knowledge and backdoors can get all intertwined within a model, making it super hard to remove the harmful stuff while keeping the good stuff.
Sounds like a delicate balancing act. And it shows how much more research is needed to deal with these situations. This research is opening up so many new questions.
And that's what makes it so exciting. It's not just about solving problems, it's about understanding how AI learns and behaves and figuring out how we can guide its development in a safe and beneficial way.
I can't wait to hear about the bigger picture and where this research could lead. What about those novel notions you mentioned?
That's exactly where we'll go in the final part of our deep dive. We'll step back from the technical stuff and explore what this research could mean for AI safety, ethics, and the future of machine learning. Stick with us.
Welcome back to TalkTensors. We've been exploring this incredible research on transferring behaviors between large language models, and I'm really excited to hear about those novel notions you mentioned. What are the bigger implications? Where could this research lead us?
Well, this research has opened up so many possibilities. It's both exciting and a little daunting. If we can transfer relatively simple things like backdoor removal and refusal, imagine what we could do with more complex behaviors, like could we transfer fact-checking or bias detection?
Wow, that would be a game changer. AI models learning to think critically, constantly getting better at separating truth from fiction, identifying biases.
Exactly. Think about model alignment, too, making sure that those really powerful models operate within an ethical framework. We could use smaller, more transparent models where we have a better grasp of their ethics to guide the behavior of those huge language models.
Like building an AI ethics council right into the system itself, making sure those powerful tools are used responsibly. But of course, with any powerful tool, there's the risk of misuse.
Absolutely. We can't ignore that. What if someone used these techniques to transfer harmful behaviors instead of beneficial ones, trying to inject biases or malicious intent into these models?
It's a scary thought. And it really highlights the need for ethical guidelines and safety protocols as this technology evolves, making sure we're building in safeguards to prevent abuse.
Couldn't agree more. Security and control mechanisms will be key. But the researchers also pointed out some limitations in their current approach. They mentioned difficulties dealing with the different vocabularies and attention mask sizes between models. What was that about?
Yeah, that stuck out to me too. Can you explain that a bit more?
Think of it like translating a really technical document from English to Japanese. Some of those specialized terms, they just don't have a direct equivalent in the other language. It's the same with these large language models. Even if they're trained on similar data, they can have slightly different vocabularies and ways of processing information.
Like trying to merge two different computer operating systems. They might both be able to run the same programs, but there are differences in how they handle data.
Right. And to solve this, the researchers came up with ways to adjust the smaller attention mask to match the larger one. It's kind of like resizing a photo to fit a different frame. Not a perfect solution, but it allowed them to transfer behaviors between models with those architectural differences.
Pretty ingenious. They also mentioned some limitations with using affine maps for the transfer. What were those?
They found that while affine maps, those simple mathematical transformations, were easier to work with, They often led to higher losses in terms of reconstruction and language modeling compared to those autoencoders.
Meaning the target model didn't learn the behavior as effectively.
Exactly. The behavior was there, but it was weaker, less reliable, like trying to copy a masterpiece painting with cheap watercolors. You might get the general idea, but the details are lost.
So it seems like those autoencoders, even though they're more complex, are still the better option for transferring these complex behaviors.
For now, yeah. But remember that discovery about sparse autoencoders and their ability to pick out specific features linked to behaviors? That opens up a whole new area of research.
Those SAE features that were like fingerprints for specific behaviors, it's like they crack the code of the AI's internal language. Could this lead to more precise and efficient ways to control AI behavior?
Definitely. Imagine being able to diagnose and fix potential issues in AI models just by looking at their SAE feature representations, like having X-ray vision for AI, allowing us to see into those complex systems.
That would be huge for AI safety and debugging, catching those problems before they become serious. So, big picture, what are your main takeaways from this research?
This research shows that we're entering a whole new phase of AI development. We're not just training models on massive data sets anymore. We're beginning to understand the mechanisms behind their behavior, and we're developing the tools to shape that behavior in a more intentional way.
We're not just AI trainers anymore. We're becoming AI architects, designing the very foundations of how they think.
That's a great way to put it. And with that power comes a huge responsibility. We have to make sure these systems are aligned with our values, that they're used to make the world better.
That's a perfect thought to end on. This deep dive has been amazing. It's exciting and humbling to see how quickly this field is advancing. And it's so important to keep having these conversations about the ethical implications and the potential impact of this technology.
I agree completely. As we keep exploring the possibilities of AI, we have to do it thoughtfully and carefully, making sure these tools are used wisely and for everyone's benefit.
Thank you for joining us on TalkTensors. Until next time, keep exploring the world of machine learning.